Alright, welcome back. In this video, we are going to look at one interesting technique, and that is integration involving the completing of squares, or integrals involving the completing of squares. Trust me, you are going to love it. Now, in our previous video, we learned about splitting the numerators and all that. Very good. But there are some times that the denominator that we are going to have is, or it can be only solved by completing the squares. Without that, you cannot solve it. Alright. We will be going right after this to what if you can't split the numerator. But that one will come in before the idea of completing of squares chip in. Alright, so let's look at that one. We are saying that what if we have, please take note of what I'm doing well. Because you can only apply the idea of completing the squares in what I'm going to teach you if only and only if you have a constant on the numerator, but the denominator is a in the form as squared plus bs plus c, whereby the quadratic on the denominator can only be solved by completing the squares. So that is what we have here. Please, the most important thing I want to emphasize in this video is that we are going to look at the case that here is a constant. We have the case that where the numerator is going to be linear, like ax plus b. And when it's linear and you can't split it, how are you going to solve that? I hope you can see that. You'll be looking at this, we'll be looking at this right after this. Because when the concept of completing the squares is clear, this one will just be easy for you. Alright. Thank you for your understanding. So let's look at that. Very good, very good. So let's look at this example. Evaluate the integral Alright, so looking at what we have, then you can see that this, you can see that with this, the numerator is a constant, and that constant is very good, 1. So for that matter, you can only solve by completing the squares, because with this you can't split it and you can't do anything with it. But we want it to be in the form of our integration table. Do you know our integration table? The one that genuinely represents something that you know already. So we go by that. So what we are going to do now is that here you just pick only this x squared minus 2x plus 5. Then you solve it by completing the squares. So you know how to solve by completing the squares. Firstly, the coefficient is, so this is algebra. Firstly, the coefficient is 1. You go and multiply by this, you get 5. With two numbers, I am just taking my time to explain this to you, but when we move on, I will not be doing that again. I will be just quoting the final answer and move on it. Very good. So, with two numbers, when you multiply, but you have to make sure that the coefficient is 1. If it's not 1, multiply by it. If it's 2, multiply by it. If it's 3, multiply by it. And even if it's 1 and you multiply by it, you get 5. And if it's negative, multiply by negative 1. Alright. With two numbers, when you multiply, you get 5. But when you add, you get this. You can see clearly that. Let's try numbers like. Alright. Let's try numbers like negative. I'm coming. Alright. Let's try numbers like negative 1 and negative 5. When you multiply these two, there is a mistake somewhere. Alright, so we take these numbers, so we take the denominator and solve by completing the squares. And how do we solve by completing the squares? Okay, so firstly, we move on to solve by completing the squares. And that is when we multiply the coefficient here throughout. And the coefficient here is 1. So when you multiply it throughout, it doesn't affect anything. Then we go and multiply half by the coefficient of the x, which is negative 2. So this is going to give us negative 1 all squared. Now, sorry, this is going to give us negative 1. But what we are going to do is that, yeah, you multiply by half, you multiply half by the coefficient of x, then you square it. So after getting this, then we are going to add to here. But what we are going to do is that we are going to create and destroy. So here is x squared minus 2x plus, then watch here, minus 1 all squared minus negative 1 squared, then plus 5. You can see that this is the same as this, just that this and this will get off. I hope you can see that. Very good, very good, very good. So that is that. So you add, then you subtract. Take note, we don't subtract and add. We add and subtract. Take note of that. And with this, you're going to get x minus 1, that's the one here, all squared, minus negative 1 squared plus 5. And that is going to give you minus 4. Sorry, plus 4. Plus 4. So that is going to be the completing of square of this side. Alright. So all that we are doing in the integration is not difficult. Just small algebra coming in here. So here we are going to rewrite this as instead of writing this, we know it's the same as this, but this is a simplified form. So this is x minus, or the factorized form, plus 4. And you know that we can write this 4 as 2 squared. 2 squared. Very good. So with this, we can do substitution, alright? We can do substitution and move on. I hope you can see that this is in the form of something that you know already. In case you have forgotten it, I don't want to just bring it like that. Let's go through it. So here we let u to be equal to x minus 1. Du is equal to, sorry, ds. Du is equal to ds. Then by substitution, we get integral of 1 over u squared plus 2 squared du. Now you can see that this is in the form of something, and that is what? Tan inverse. Very good. So this is just a straightforward. It's in the form of tan inverse. Very good. So therefore we write, and don't forget it's 1 over, let me make that correction. It's 1 over a, and that a is 2. So 1 over 2 tan inverse of u over a. And the u now is x minus 1 over a, which is 2. So that is actually tan inverse. That is actually tan inverse. So we conclude and add plus c. Alright. So just don't forget that it's something that you know already. In case that you have the numerator to be a constant and the denominator to be quadratic. The only thing that you can solve is to solve by completing the squares. And that is how we solve by completing the squares. It's not difficult. When you get to this side, it will always be something that you know already. Whether trig substitution, integration by parts. By part normally come in here. It's just going to be easy for you. Let's try on our second question. And please take notes. Let me emphasize this. Let me emphasize on this. There are some of these that when you punch on the calculator, you will be getting a complex numbers. All right, you'll be getting complex numbers. So that should tell you that you can only solve by completing the squares. If it don't give you complex numbers, that means that it can be factorized, and you can factorize it and go and do integration by partial, because once it's able to factorize, then it can be whether a repeated factor, a linear or whatever. So if it can be factorized, then that can be solved by integration of partial decomposition. Integration of partial decomposition. So sometimes you need to think around and check the alternatives if that is going to be helpful. All right, very good. Looking at this, now with the denominator here, this actually by completing the squares, because we have a constant here, and without the completing of squares, you can't solve this. You can't solve this by splitting, not by anything. Now you can see that with this, can this be factorized? Can you solve this by factorization? When you multiply 1 by here, you get 10. And with two numbers, when you multiply, you get 10. But when you add, you get plus 2. No number. There is no number. And if there is no number, that means that this can never be solved by factorization. One factorization will, then integration by partial decomposition will help you. But here, factorization is not working, so we go by completing the squares. Obviously, very good. So by completing the squares, make sure that the coefficient here, you divide by it. So here is 1, here is 1, here is 1. The reason why I I don't want to write over 1 is that over 1 will not affect anything. But if it's 2, don't forget to bring it. If it's 3, don't forget to bring it. Alright? Very good. Then you multiply half by the coefficient of s, which is 2. Then you square it. So with this, you get 1. So you get s squared minus 2s, sorry, plus 2s. Then you add this, then you subtract plus 10. Very good. So having this, you can see that you're going to get s minus 1. Sorry, here is plus. So s plus 1 squared. You can link this to the previous one that we solved. We having here to be minus. That's why here was minus. So, and the whole of this, I think you're going to get negative 9. Sorry, plus 9. Alright, so that is what you are going to get for that. And by substitution, we end up getting s plus 1 squared plus 3 squared. And the reason why I'm leaving it 3 squared is that it's resembling something that I know already. Alright? And that is surely tan inverse. So you can go and do substitution. Let u be s plus 1, du will be equal to ds. You come and do the substitution back. u square plus 3 square dx. Alright. So you write tan inverse of u over a. But don't forget that here will be 1 over a. Most at times students forget. Please don't forget. And here is 1 over 3 tan inverse of x plus 1 over 3. And that's going to be the final answer for that. Then you add plus c. In fact, if you know a tan inverse, you can just quote it straightforward and go your way. Alright, so that is that for that. And you can try your hands on some of these questions relating to the idea that we have just shown you. Relating to the idea that we have just shown you. Alright. It's still the idea of completing the specs, evaluating the integral. Please, it's not always that when you get to this part, when you get to this part, you're going to be tan inverse. It can be sine inverse, it can be sine inverse, tan inverse, and the other one. I think I've forgotten it. Alright. And there are sometimes that it will not resemble any of them for you. So the only thing that you do is that you go by trig substitution to solve it. So when you get to this part, it just link it to your previous knowledge and you are going to get it. If only and only if you have gone through all my videos on this channel, then these things shouldn't be anything difficult for you. Alright. So evaluate the integrals. A nice question to be. Now, with this, it's straightforward, completing the squares. So don't worry yourself about this, okay? Don't worry yourself about this. After everything, you see that it will be in a form that you'll be using your idea of trigonometric substitution. And I have taught you that, so you don't need to worry yourself. So we are going to pick this one, complete the squares, come and do the substitution back. You have, in case it's not in a form of something that you know already, then you apply trig substitution or any of the methods. Now watch, with this, clearly you can see something here. And I hope you can see what I'm seeing. It's not that anytime you have, now this is not in the form of this, so you have to think through this one more. It can be that this will not be, even though it will be the idea of completing the squares, you can use that. But something is chipping in here first. You see, let's look at setting this to be equal to. When you take the derivative, watch, when you take the derivative, you get negative 2x plus 10. Hope you can see that. And when you, hope you can see what I'm saying. And when you factorize negative 2 out, you get s minus 5. Wow! And this s minus 5 is exactly what we have here. I hope it's clear. So you end up getting this to be, you know that the whole of this is going to be square root of u over this. and you know this to be, you have that, alright. So you know that here is x minus 5. Alright. Now let me bring the ds here. Du is equal to the ds. So what should be ds? Ds should be du over negative 2s minus 5. Alright? And you can see that with this, you can't do anything about it, you see. So somebody may be thinking of doing it in this way. Please, such is not going to help you. You are going to have a problem on your way. So this method is not going to help. Alright. So what is going to help is only by going with the method of completing the squares. So it may be that someone will be thinking of this way. That's why I have shown you that such is not going to help you, because if this come on top, then this can cancel this, then you go your way. But so far as this is not coming on top, then it's going to be something tedious for you. And if you want to go and make any subject before you come and do the substitution, you will just end up committing errors. Alright, so such can't happen. It's only when you pick the inside, complete the squares. And right after completing the squares, then you start by doing your substitution. Alright. And the good news is that the completing the squares, you're going to get something inside which will resemble this. What about this one? Alright, this one is also going to be nice to you. This one is also going to be nice to you. Last one. Just complete the square of the inside and apply this substitution and go your way. Now, it's not always that the numerator is going to be a constant. Sometimes you get 8. Sometimes you get 8 not in a form of a constant. Sometimes you get 8 not in a form of a constant. But since you're good in your trig substitution, wherever you factorize these to get, you can still go with it with the method of trig substitution. So please, be bold enough to continue with this. Alright? And you can. I said you can. Very good. Now, I think that is all for that. That's all for that. It's all about you knowing how to do your trig substitution. And sorry, it's all about you knowing how to complete the squares and do the substitution. That is all for that. Alright, so in our next video, we are going to look at the case whereby we have a linear equation on the numerator. A case whereby we have a linear equation on the numerator. See you for that video.